Welcome you all to the crash course of chemistry. Today we'll start with the topic occurrence of metals in continuation of the chapter metals and non-metals, right? So the first thing is, how do metals occur in nature? We use several metals. They are available in various, basically in two ways. Either they are available in free state or they are available in the combined state. The ones which are less reactive or least reactive are in free state, and others are in combined state, like silver, gold, platinum. These three metals are in free state because they are least reactive. And aluminum, calcium, zinc, sodium, these all are in combined state. Like we get aluminium as aluminium oxide, calcium as calcium carbonate, zinc in zinc carbonate, sodium in chloride form, like that. Copper can exist both in free and combined state. So just now, as I told you, combined state means the compound form of the element. Now, so now let us see the questions based on this. The question is, you have to name two metals which are found in free state and two which are found in combined state. So you can give any example here, like gold, silver, platinum are the ones which are least reactive, so they are found in free state, and in combined state you can give any example of the one which we discussed just now. Now, there are three terms: minerals, ore, and gangue. These are related to the metals and the impurities. The minerals are the naturally occurring materials or the metals which are in the compound form. And in the minerals, the elements are present in very trace amount, in very less amount. So we will be able to extract metals from minerals, but it will be very costly, because minerals have less content of metals, and ores are the materials which have high amount of metals present into it. So it is profitable to extract metal from the ore. The valueless or the waste material which is present in the ore other than metal is called gangue. Now, there are some examples of ores given here, which is asked for 1 mark. Like aluminium is available in bauxite form, which is aluminium oxide. Copper is cuprite, that is copper oxide. Then we have calcium available in limestone, calcium carbonate. The metals mostly are in oxide form, because oxygen is abundant in the environment, 21%, and metals react readily with the oxygen. So we have, most of the ores have oxygen in them. Zinc is available in calamine form, that is zinc carbonate. We have zinc blend also, which is zinc sulfide. Copper is copper glance, copper sulfide. Sodium is available as rock salt, sodium chloride. And finally, we have fluorspar, which is calcium fluoride. So here, one example of each ore you need to remember, because as I told you, it is a 1 mark question. Now, when the minerals are taken out from the earth, they have whole lot of impurities into it along with the metals. So we need to get rid of the impurities so that we can get the metal in the free form or the pure form. So this all is a part of metallurgy. So let us see now what are the steps of extracting metals. The first thing is mining out the ore of the soil. These huge machines are there which take out the ore from the soil, and then the crushing of the ore is done. Sometimes the ore is in huge boulders form or rock form. So it needs to be crushed into powdered form. So these are the machines which crush these rocks into smaller particles. It still is not in the powdered form. So we have one more machine here, which is called pulverizer, which grinds the small pieces into powdered form. And after that, the concentration of the ore is done depending on the metal present into it. Sometimes concentration is done only by washing it with water. And after the ore is concentrated, it is made to undergo a treatment depending on the type of the metal. Like metals are in three main categories. You can see these three categories of metals. They are highly reactive, moderately reactive, or low reactive. So depending on the type, there are various steps. Let us see. Now this is the reactivity series. The metals which are below hydrogen are least reactive: copper, silver, gold, platinum, mercury, and so on. These metals are least reactive, so simply heating them is enough to obtain them from the ore. Let us see the example. As I told you, they are available in oxide or sulfide form, so we simply heat them. Let us understand with the help of an equation. You can see here mercury sulfide. Mercuric sulfide. You are heating it in the presence of oxygen. So what happens? Sulfur gets away in the form of sulfur dioxide and we get mercury oxide. If we continue heating this mercury oxide, we get mercury in free form. You can see here, mercury is available in the free form. So this process during which the ore is heated in the presence of oxygen is called roasting. This process is called roasting. So this mercuric sulfide is also called cinnabar. The common name of this ore is called cinnabar. So you can have a question asking, name the mercury ore and how the metal is extracted out of it. So only roasting is enough. Then another example is copper sulfide. Again, this one is being roasted in the presence of oxygen and we are getting copper oxide. If you continue heating it, you get copper in free form and sulfur dioxide is away. So these four equations you need to remember when you have to answer the question, like explain how metals of low reactivity series are extracted. So these are the four equations given here. The definition of roasting is when you heat ore in the presence of excess of air is called roasting. So one step is done, one group of metal is done. Now we see the next group, the middle group between carbon and hydrogen. These are moderately reactive metals. And these are available either in oxide, sulfide, or carbonate ore. Now, it is easy to extract metal from the oxide ore instead of sulfide and carbonate. So what is done here? Carbonates and sulfides are first converted into oxides. So we'll understand this with the help of example of zinc. You can see here the equation is showing zinc carbonate here. Zinc carbonate is being heated and you get zinc oxide and carbon dioxide. If you see this equation carefully, you will notice that the presence of oxygen is not there. It means this ore is being heated in less amount of oxygen. So when you heat it in less amount of oxygen, This process is called calcination. Calcination. So zinc carbonate is made to undergo calcination so that it can be converted into zinc oxide. All right. So you need to remember the process. Calcination is heating metal carbonate in the less amount of oxygen to convert into zinc oxide. Now we converted carbonate into oxide. Let us see what do we do to the sulfide ore. This is zinc sulfide there in front of you. You are heating this in the presence of oxygen. So it is roasting. Few slides back we discussed heating in the presence of oxygen is called roasting. So zinc sulfide is roasted and we get zinc oxide along with sulfur dioxide gas. So the two ores of zinc, zinc carbonate and zinc oxide, were calcinated and roasted to get zinc oxide, right? So we have reached the oxide. You can see here, this was the path that we discussed just now. Carbonate calcination, sulfide roasting, and we got zinc oxide. Now, what are we going to do to the zinc oxide? We'll take this zinc oxide and we'll reduce it because we don't want oxygen here. We simply want zinc. So reduction is to be done. Now to reduce, there are two ways. We cannot heat it and reduce it. We have to use a reducing agent, a suitable reducing agent. So it can be carbon or other highly reactive metal. Any of this we can use. We can either use carbon for roasting or we can use another highly reactive metal. So when we use carbon, zinc oxide converts to zinc and we get carbon monoxide gas. This process is called smelting, where zinc oxide is reduced to zinc with the help of carbon. This process is called smelting. Okay. Now, uh, both are taking place here, reduction and oxidation. We can see another equation also for the same group. Iron belongs to the same category. Carbon is being used here to reduce it to iron and carbon monoxide. So reduction is taking place here, right? Now, if we use another more reactive metal, like here we can see an example of manganese dioxide. This belongs to the same category of moderately reactive metals. Aluminium is used, which is more reactive than manganese. So what happens? It will displace manganese. We get manganese in free form with the aluminium oxide, and lot of heat is generated here. So this process is highly exothermic. This process is highly exothermic because we can see a lot of heat is produced here. Now this heat is enough to melt the metal. This manganese which is produced here, it is in molten form. It is in molten form because the heat produced here was enough to melt it. So this is the characteristic feature of this reaction, right? You can see here reduction is taking place and this is oxidation because aluminium is gaining oxygen and manganese dioxide is losing oxygen. So this is the redox reaction, exothermic reaction, displacement reaction. It can be categorized in all these ways, right? So as I told you just now, that the high amount of heat energy produced here will make the metal melt, and this reaction is used practically in welding. You can see the equation given here. Iron oxide. This iron oxide is made to react with aluminium. So aluminium being more reactive than iron displaces, converting in aluminium oxide, and iron is free. Again, the heat produced here makes the iron melt. So This reaction is used in welding. Welding is the process of joining the metal parts. Joining the metal parts. Okay, joining the metal parts. Like especially the railway tracks. The railway tracks which are having crack in them, they are weld using this reaction. So this is one of the use of this equation, this reaction. So this is called thermite reaction. All right. Because here aluminium is used as a reducing agent, this reaction is called aluminothermy. The reduction where aluminium is used is called aluminothermy. Now we have a question here. What chemical process is used for obtaining a metal from its oxide? So we've seen just now, reduction is used to get the metal from its oxide form. And to reduce, you can have any reducing agent. It can be carbon or any highly reactive metal. So example is given here for zinc. Then we have another question. It is asking you metallic oxides of zinc, magnesium, and copper were heated with the following metals. In which case will you find a displacement reaction taking place? So the table is given here. Now, if zinc reacts with zinc oxide, will you see any displacement? No, the displacement will not be seen. What if magnesium reacts with zinc oxide? Yes, displacement will be seen because magnesium is more reactive than zinc. Copper and zinc oxide will not give this displacement because copper is less reactive. So in this way, we can answer the question. Zinc and magnesium will not show any reaction. Magnesium and magnesium oxide will not show reaction. Copper will also not show any reaction with magnesium oxide. Zinc will displace copper from copper oxide. Magnesium will also displace, but copper will not displace copper oxide. So this is depending on the reactivity series. Now we'll see the metals which are most reactive, which are high up in the reactivity series. The example that we discuss here is of sodium. Now it is very difficult to extract these metals. You cannot use simple methods like heating or reducing them using a reducing agent because they are most reactive metals. If you heat them at a higher temperature, they will convert into carbides. Then it is more difficult to extract the metals from the carbide form. So here the only method left is using electric current. You can simply use electric current to extract them. Let us see this with the help of an example. Here we are using the example of sodium chloride. Now sodium chloride is in solid form. The first thing done here is it is heated so that it converts to molten form. You can see this liquid molten form, right? Now, when this sodium chloride is in molten form, the ions are free to move. The ions are free to move. Then it becomes easy to direct them. As I told you, the ions are free to move. So we can direct them. How to direct them? So we need to pass electric current. You can see in this diagram, this is molten sodium chloride. And these are the two electrodes. These are two electrodes. They need to be connected to positive and negative terminal. You can see the circuit here. This electrode is connected to the negative terminal, so it becomes the cathode, and the other one is connected to positive, it becomes the anode. Now, when the current is, when the circuit is joined over here, sodium ions, which are positive, Na plus, they get attracted towards the cathode. And chloride ions, Cl minus ions, which are negative, get attracted towards the positive electrode. Now, sodium ions go on depositing on the cathode because they are getting deposited in the elemental form. Na plus is gaining electron to become sodium. Now, gain of electron is called reduction. So, sodium ions are undergoing reduction at cathode, and they are depositing in elemental form. At anode, chloride ions are losing electrons to become chlorine gas. Two chloride ions are losing two electrons to become chlorine gas. Now, the loss of electrons is called oxidation. So at anode, oxidation is going on, so that chlorine can be converted into elemental chlorine, that is gas form. So here you will see bubbles of chlorine gas escaping at this electrode, right? So when the process is going on, you will gradually see sodium depositing on cathode, and after some time when you switch it off, you can take the electrode and you can scratch the sodium out of the surface. So basically here we were able to extract sodium from its chloride form by using electric current. So this process is called electrolytic reduction. Electrolytic reduction, because the sodium ions underwent reduction during extraction. These are the two equations that you see, the one which I explained just now, happening at cathode and anode. At anode, oxidation is taking place, and at cathode, reduction is taking place for sodium. So in this way, the extraction of sodium, a highly reactive metal, is done. I would like to recall you the one of the concept that you have studied in second chapter, sodium chloride. Here, to extract sodium chloride, sodium from sodium chloride, we took it in molten form and we passed electric current through it. But if you take aqueous form of sodium chloride, and when you pass electric current through it, we get sodium hydroxide, chlorine gas, and hydrogen gas. This is called chloralkali process. This is called chloralkali process, which we discussed in the second chapter. So you have to be very careful when you are writing the answer. If you are asked chloralkali process, you have to take sodium chloride in aqueous form. But if you have to extract sodium out of sodium chloride, then you have to take the molten form. So you have to be careful while writing this answer. Okay. Now, the metals that we have extracted so far are not very pure. They might be 99% pure, but not completely pure. So we need to refine them. We need to purify them. So now the next topic that we are going to discuss is about the purification of metals. This is called refining of metals. Again, for this process, we will be using electric current. So here we'll discuss the example of copper for refining of metal. Uh, you can see a beaker is shown here. This contains acidified copper sulfate solution. Copper sulfate is CuSO4 in aqueous form. It is having few drops of acid into it to make it all the more best conductor of electricity. Copper sulfate is an electrolyte, but to make it very good conductor, a few drops of acid are added into it. Okay. Then two metal rods are taken of copper. One is impure metal rod, and another one is pure metal rod. The impure metal rod is made anode, and the pure metal rod is made the cathode. Now, how to make it anode or cathode? By connecting it to the positive or the negative terminal, right? Let us see the circuit. So uh, you can see here the this is impure. This one is impure copper rod. So it is connected to the positive terminal of the battery. And this is pure copper rod. It is connected to the negative terminal of the battery. So it is called cathode and anode. Now, when the circuit is joined like this, the current starts passing through the electrolyte, and the ionization of copper sulfate takes place, and it changes to Cu plus 2 SO4 minus 2. Copper sulfate breaks down into copper and sulfate ions. Now, copper ions being cations, these Cu plus 2 being cations get attracted towards the negative electrode, the cathode. They get attracted towards the cathode and they start depositing over there. Now, the equal number of copper ions which from the solution are going to cathode start coming out from the anode into the solution. Equal number of ions start coming from the anode to the solution to maintain the equilibrium. So in this way, when the process goes on, copper ions are depositing on cathode, and from anode the copper ions are coming into the solution. So what happens is this anode keeps on decreasing in size and cathode goes on getting thicker because copper is depositing on it layer by layer it is depositing on the cathode. So a time comes when this completely gets disappeared because all the copper has come into the solution, the circuit breaks and the process stops. But when this is happening, the impurities which were there on the anode just fall here and they gather here just below the anode. This is called anode mud. Anode mud. The impurities which settle down below the anode is called anode mud. Right? So you can see this impurities. Okay. So this is the diagram which makes it clear that the anode is decreasing and cathode is increasing in size. So during this process, all the copper from the anode has got deposited on cathode and the refining is done. The impurities have gone away. So the refining is done using electric current. Now the question says, in the electrolytic refining of a metal M, what would you take as cathode, as anode, and the electrolyte? So if metal M is there, the anode will be impure form of metal M. The cathode will be pure metal M, and the electrolyte will be the salt of metal M. The salt of metal M. Right? The way we discussed just now in the previous slide. Now you can see the silver metal becoming black over here. This is the copper metal becoming green. And this is the iron metal which has got rusted becoming brown. So this is corrosion of iron, silver and copper. So let us see now what happens when they get corroded. Silver reacts with hydrogen sulfide. This is silver over here. It reacts with hydrogen sulfide to give silver sulfide, and hydrogen is free here. So this basically, this silver sulfide is responsible for the corrosion of silver, which makes it go black. Then for copper, becoming green is the corrosion for copper, and here carbon dioxide is responsible because copper changes to basic copper carbonate. Basic copper carbonate when it gets corroded and it becomes green. And iron reacts with the moist oxygen to become iron oxide, the brown flaky layer which is called rust. So you need to remember these three examples here. There is an activity given in your textbook. It says that you have to take some iron nails and 3 test tubes you have to take. Now, in these test tubes, you have to take water. In the first one, you have taken water. In the second one, you have taken boiled distilled water with a layer of oil on it. Now, when you boil the water, whichever oxygen was present in water gets removed. And then you have a layer of oil so that no more oxygen can dissolve. No more oxygen can dissolve into. It means there is no oxygen in this water. Okay. And the third test tube you are taking is with an empty test tube, obviously having air into it, with some calcium chloride into it. Now, this will not have any moisture into it because it has absorbed all the moisture. It has absorbed all the moisture from this. So it simply has oxygen. It simply has oxygen, right? And in the first test tube, you have air, means oxygen is there and water is also there. Now in all the 3 test tubes, you are putting the iron nails. So now let us see what happens. The first test tube where iron air was there, it has both oxygen and water into it. So it got corroded. The second test tube where there was no oxygen available, oxygen was not there, did not get corroded. And the last test tube where moisture was not there, no water, that also did not corrode. So this activity shows that the presence of both, that is oxygen and water, is required for the iron to get rusted. For the iron to get rusted, only water is not enough, only oxygen is not enough. We need both iron and oxygen and water, both for the rusting of iron. The metals which do not corrode easily are the least reactive metals like gold, platinum. How the iron rusting of iron can be prevented? You can do painting, oiling, greasing, any which way you have to cover the surface of the metal so that you avoid them coming in contact with oxygen. You have to block the oxygen supply or the supply of moisture. Galvanizing is giving a coat of zinc. Chrome plating is giving a coating of chromium metal. Then anodizing is covering it with a layer of aluminium oxide. Making alloy is mixing different metals to give to change the property, right? So these are some ways by which you can prevent corrosion. You can see the person is painting the grill, oiling or greasing. This you must have experienced while greasing your bicycle parts. Galvanizing, this is the iron object which is being dipped into molten zinc to give it a coat. This is silver plating. The spoon is being given the coating of silver metal. Anodizing, as I told you, it is giving a layer of aluminium oxide. Aluminium oxide is a tough layer. Uh, it will not let the metal get corroded, which is beneath. Alloying is mixing two or more metals, or sometimes a non-metal is also mixed with it. So we have certain examples here. Iron can be converted into stainless steel because iron is a metal which gets corroded or rusted easily. But if you mix a small amount of carbon, like 0.05% carbon into it, it will not get rusted, and it is called steel. If you mix nickel and chromium into it, it becomes stainless steel because it will never rust and it is hard in nature. Then you have another example of brass, which is an alloy of copper and zinc. We have bronze, copper, and tin. So these are solder is the alloy of lead and tin, which is a low melting point alloy. It is used in soldering the circuits. Then amalgam is the alloy of mercury, where mercury is used as one of the component. Now mostly it is used in Dalton amalgam to fill the cavities because it is highly bacteriostatic. It will not get infected by bacteria. It is durable and it lasts long and low cost. So and it is suitable to be there in the teeth. So this is about the alloys. So this is the question why copper is used in making hot water tanks and not steel, because steel is an alloy of iron. It will react with steam and it will get corroded. So copper is used, steel is not used over here. This is the equation showing the rusting of iron, right? Then you have what are alloys? Alloys are homogeneous mixture of two or more metals, or sometimes a metal and a non-metal. Examples we have seen just now. Then which of the following is suitable for preventing iron frying from getting rusted? Applying grease, paint, coating of zinc, or all of the above? So applying zinc is the most suitable answer. Platinum, gold, and silver are used to make jewelry because they are lustrous metals and they are least reactive, so they don't get corroded easily. Sodium and potassium are stored under kerosene because these are highly reactive metals. They react with oxygen and they catch fire. So to avoid these accidents, they are stored under kerosene oil. Aluminium is highly reactive metal, yet it is used to make utensils because it makes a layer of aluminium oxide which stays there on the metal and it prevents its rusting. So aluminium is used in this. Carbonate and sulfide ores are usually converted into oxides because it is easy to extract metal from oxide rather than carbonate or sulfide. So carbonate ore and the sulfide ore is first converted into oxide and then the extraction is done. You must have seen tarnished copper vessels being cleaned with lemon or tamarind. Explain why these sour substances are effective in cleaning. Because tarnished copper vessels are having a corroded layer of basic copper carbonate. So it will react with the acidic substances like lemon or tamarind, and it will neutralize the layer, and the new layer gets exposed, which is shiny. So basically, to remove the basic copper carbonate from the surface, this is done. So here we end the